Hello and welcome to Contemporary Math lesson for section 3B, putting numbers in perspective. And this lesson will get into what we will call scientific notation. And scientific notation, as you can see right down here, and how scientific notation works is there will always be two parts, a number between 1 and 10, and a power of 10. And the operation here will always be multiplication. And usually what ends up happening is you see this scientific notation to represent either very large or very small numbers. And it's just easier to write them in this form than it is with a bunch of zeros. So let me get an example right in this area here. So here I have a lot of 3.54s. And they're all being multiplied by different powers of 10. So what would this look like? So here I have marked 3 quick calculations. And you can see that the higher the exponent for the 10, the more places this decimal moved. So for these up here, as we increase the number of, the power of 10, and it's positive, this moves the decimal point to the right. So you can see it started out here between 3 and 5. And if you move it 1, 2, 3, 4, 5, 6, 7, 8, 9 times to the right. And that will create this monstrous number here. I think it's 3,540,000,000. So when you see this with the 3.54 in the second example here, and the exponent being 4, it started here, it moves 1, 2, 3, 4 to the right. Now, this one in the middle, everything stays as is. 10 to the 0 power is 1, as anything to the 0 power is 1, except for 0. 0 to the 0 power is who knows. So that leaves these down here. What a negative exponent does is it moves the decimal point left. So again, it started here between 3 and 5, and it moved 3 to the left. 1, 2, 3 to the left. And the same thing here, it moves 7 to the left. 1, 2, 3, 4, 5, 6, 7. However, you don't want to be writing all these zeros, so we just use scientific notation to shrink it down. So let's take a look at how to actually do this. We want to convert to scientific notation, and we want to convert from scientific notation. And so you'll notice things move a little bit differently. So above, when I was doing examples up here, I was converting from scientific notation. So let's continue with that idea. So just to get some more practice here, if the power, step 1, the power of 10 indicates how many places to move the decimal point. You move it to the right if it's positive, you move it to the left if it's negative, just like I did up in this example up here. If moving the decimal point creates any extra open places, fill them with zeros. So just a very quick couple examples, and then you can try these two down here. 3.12 times 10 to the 7th, 3, 1, 2. The decimal points here, I'm going to start 1, 2, 3, 4, 5, 6, 7. So I moved it 7 times, filled all these in with zeros, and that's the number. That would be 31,200,000. And for this particular example, because there's a negative exponent, I will be moving it to the left. So 738, the decimal point is here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the decimal point would be here. Fill all these in with zeros, and go ahead and try these. Hopefully you paused the video and you were getting these two answers down here. The positive exponent tells you to move it to the right, 1, 2, 3, fill in with a 0. The negative exponent tells you to move it to the left 4, 1, 2, 3, 4, fill those in with zeros. So now that you're all familiar with that, I'm going to go ahead and break your brains when you convert to scientific notation. So we're just going to go in the opposite direction. We're going to do exactly everything backward. So if you have the entire number listed out here, and you're trying to put it in scientific notation, then you have to do everything backward. So for example, here's the decimal point for this one. I have to move it left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And I have to go all the way to here because I'm looking for a number that is between 1 and 10, but it cannot be equal to 10. So if I move the decimal point all the way over there, I will have 1.95. So how far did I move the decimal point? I had to move it 13 spaces. So that means I would have to raise this times 10 to the 13th power. Read very carefully. It says move the decimal point to come after the first non-zero digit. Then for power of 10, use the number of places to the decimal point moves. The power is positive if it moves left and negative if it moves right. So let me prove this to you. So this is a good answer here. Let's try this. So here, this is the decimal point. This is a period. So this is the decimal point here. So I'll move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I have to go all the way until it is to the right or just after the first non-zero digit. So this is 15 places. The first non-zero digit was 1, and since I went to the right, this has to be negative. Go ahead and try this one. You should get 3.24 times 10 to the 8th, and normally we just round these numbers to 2 decimal places, so that's why I only have 3.24. It kind of defeats the purpose to go all the way out to 3.24227 when you're trying to shorten the notation here. So there is converting to and from scientific notation. So with this particular slide, we will go over how to manipulate with operations for scientific notation. And all that means is that we're going to, like operation is just multiplication or division, like down here. And it's very, very simple. So the first thing we have to do is just multiply the 6 times the 4. It's normal multiplication. And we're going to leave it in scientific notation, so we don't have to worry about that. But we will multiply this by 10 to the 12th power here. And how do you do that? So when you multiply powers of 10, add the exponents. So the 5 and the 10 here get added, or sorry, the 5 and the 7 here get added together and equal the 12. So that's how I get 5 to the 12th, but now we have this issue. You can see the number we started with is between 1 and 10. The number we started with is between 1 and 10. This number is not between 1 and 10. That decimal point is right here though, and we have to move it to the left 1 place. So if we move a decimal point 1 place to the left when we're trying to write it into scientific notation, that will make this 2.4, but that will add an exponent, add 1 to the exponent here. So very similarly, with this second example down here, you will subtract powers of 10 when you divide. And this is easy enough. All you have to do is subtract the exponents in this form, top minus bottom. So just like we multiplied the two numbers that were up here, we're just going to divide these two numbers that are right here. And if you just type it into a calculator, 4.2 divided by 8.4 is 0.5. And I'm going to write this out a little more explicitly with these powers of 10 because they're both negative. But 5 and 7 was pretty easily added to 12, so I didn't hesitate with that step up there. But what would happen here is we would have 10 minus 8, or 10 to the negative 8 minus negative 12. And subtracting a negative here is exactly the same as adding a positive. So we would have here 0.5 times 10 to the fourth power, because negative 8 plus 12 is 4. Now here's something else we have. This number, you always got to be on the lookout, is not between 1 and 10. So we have to move the decimal point to the right one time. And if ever you're moving a decimal point to the right in scientific notation, just like we did the opposite of here, moving to the left was adding 1, moving to the right would be subtracting 1. So this would be 5 times 10 to the third power. All right, so down these last few examples here are trying to guide you to understand how to work with large numbers and how to operate with them. So one thing that you want to do is notice that this number right here, 296, is not going to be the nicest number to work with. It's going to be 2.96 times 10 to the, what is that, 8th power, and I'll get more into that later. But that is, like, decimals here are not going to be that nice to work with. And since we are working with such large numbers that need scientific notation, or would be easier to use scientific notation, we can round them. So what we can do here is round to 4 trillion times 300 million. And what that'll do for us is it will eliminate all the decimals and just make the math a little bit easier, and we won't even be that far off at the end. So how will this look in scientific notation? Well, 4 trillion looks like 4 times 10 to the 12th power, and 300 million will look like 3 times 10 to the 8th power, which again is a lot cleaner than what we had up here. So now all we have to do is just multiply these two together, and we can get our final answer of, what is this? 4 times 3 is 12, times 10 to the, we add the exponents since we're multiplying, that'd be 20, but we have to move the decimal point 1 to the left and say 1.2 times 10 to the 21. So we had to add 1 to the exponent for this decimal point move here. Now the actual answer, if you leave it at 296 million, is 1.184 times 10 to the 21st. And I'm going to go ahead and say these two are not that far apart from each other. It's 10 to the 21st. There we go. These two are not that far from each other as far as the big numbers are concerned. All right, so for this last example on this slide, our nation has a debt of approximately this much. You should not even be worried about your student loans at this point. This amount of money is ridiculous. So the population of the US is this much. If everyone in the country had to contribute money to pay off the debt, how much would each person have to pay? Now, I like this question, but I also don't like this question because this includes babies that are minutes old, and it doesn't make sense for them to be paying, but it's always fun to think about these types of scenarios. So we think we've already worked with this number on the previous slide. Yes, we sure did. And this ends up being 1.95 times 10 to the 13th power. And I think we also dealt with this number on the previous slide. It ends up being 3.24 times 10 to the 8th power. So if you divide the numbers like we did on the previous slide, we would end up with 0.60, and again, we're sticking with our 2 decimal places. And we would have to just do our quick subtraction. I'd say top minus bottom. 13 minus 8 is 5, so it's 0.60 times 10 to the 5th. But since we are moving the decimal point to the right, we will subtract 1, and that'll give us 6 times 10 to the 4th power, which is, and this is all approximate because we're rounding here, this is about $60,000 per person. That's it, $60,000 per person, and the whole United States could be out of debt. Start paying up, everybody. So with this last slide, we're here just to get some perspective through making it understandable, I guess, how long it would take to count to these large numbers, or just get some sense as to how big, really big these numbers are. So consider 100 billion. This is a lot of money. A number that you may find in the news almost any day. Big banks, big corporations, maybe even Bill Gates. I don't know how much money he's worth at this point in time. It's easy to say it's big, but how big? So let's say you were asked to count $100 billion in $1 bills. How long would it take? Well, we would assume that you would count $1 per second, and it would take then 100 billion seconds. Well, using the unit conversion that you've already learned, this would be 1 times 10 to the 11th, or in this case, if you ever just end up with 1, it's just 10 to the 11th seconds. Well, we want to cancel seconds. We're trying to make this into something useful here. So how about 1 minute for every 60 seconds? And we can cancel out minutes. We can say times 1 hour for 60 minutes. So the minutes would cancel here. The seconds would cancel here. Let's see. Let's multiply that by, what is that? 24 hours in 1 day. So I need hours to be on the bottom, so they'll cancel. That would be 1 day. Well, I don't think days is going to do it either. Let's go. I want 365 days per 1 year. And if you go through and figure all this out, it's going to be approximately 3171 years. Yeah, that's right. It's going to take like 50 generations easy. I don't know how many generations that would take. It would take a lot of generations. Probably closer to 120 generations. Yeah. To count out all this money. So don't try it. But that should give you some perspective as to how big 100 billion is. So let's say in this next example, you become a sports star and earn a salary of $1 million per year. You know what? We're in whatever year this is, 2020. Let's make it 10 million per year. That's not unheard of. How long would it take for you to earn $1 billion? Well, if you know 10 million is 10 to the 7th power, and you know 1 billion is 10 to the 9th power, we could just divide these. 10 to the 9th over 10 to the 7th. So all we have to do is subtract these exponents, top minus bottom, which is 10 squared, which everybody knows is 100 years. And I think even the best athletes, even the NFL kickers, their best season, maybe 21 seasons, or for 21 years, there's no way it can happen. No way it can happen. So again, just to put some perspective onto this. And so for this last example, putting it all together, consider we have a university and there are 25,000 students. That's a lot of students. The number 25,000 is small compared to many of the numbers we've dealt with in this chapter, but it still takes thought to put it into perspective. So imagine that the new university president wants to get to know the students and proposes to meet for a lunch with a group of 5 students at a time. Is it possible for her to have lunch with all the students? Well, in this example, I don't think we need to use scientific notation. But so we can just do something like this. We can say there are 25,000 students, and she'll meet with 5 every day for lunch. So that means she would need 5,000 days. Now, this still doesn't make too much sense here because 5,000 days can be crunched down into something like 17 years or something like that. But you may understand if you're out there in the workforce that you generally only work 5 days a week, Monday through Friday. So let's divide this by 5 days per week, and that gives us a total of 1,000 weeks. And again, that still maybe doesn't make a whole lot of sense to you, but what we can do finally is we can divide 1,000 weeks by 50 weeks per year. And again, the general idea here with the 50 weeks per year is that this is a nice round number and it works better than 52 weeks in a year. And generally speaking, people get about 2 weeks vacation or maybe 2 weeks worth of sick time or some combination thereof. So 50 weeks makes a whole lot of sense. So this would take then about 20 years. Would she be able to meet with all of the students? Not unless they were all very, very dumb and very, very rich. So here the answer is no, she would not be able to get to know all of her students. Again, just to keep some numbers in perspective.